All right, well, thank you for joining us here for our review. Really, the way I think of this quiz coming up is divided into three sections. There's a section where you need to understand energy calculations, you need to understand how to compare the strength of IMFs or intermolecular forces. And I also want you to understand the difference between polar and nonpolar substances. So hopefully you've had or been working on this practice quiz. You can find those solution guides. Hopefully you've been to our class website and can see the practice quiz answers. The other materials that you want to have completed before the quiz, really those energy calculations from a couple weeks ago are very worthwhile, good practice. There's a lot of good vocabulary and a lot of good introduction to these chemicals and the properties of liquids. That was where we squirted acetone on a penny, glycerin on a penny, uh, water on a penny, and then we would try to float the paperclip on water, if you remember playing around with that activity. The soap, the drawings in that soap article are real important to kind of be able to recognize. And please remember, the only thing I'm collecting besides your quiz is the soap article questions. So make sure you get those done when you take the quiz. When we dropped that cube of metal into our styrofoam cup of water, that has a lot of good problems and questions on it as well. I gave you a packet just kind of called Delta H homework. I really like a lot of the examples in that one. So those assignments are really what I used to put together this practice quiz. And then also, once again, what I'll use to put together the real quiz that you'll be taking. Okay, so once again, please be using our website to help you review. All right, so once again, the quiz is really, I think of it as three parts. There's energy calculations, there's IMF, intermolecular force comparisons, and there is deciding what's polar, what's nonpolar. All right, so for the energy calculations, now remember you're given this information for water. So it's Q, 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 Q. Q stands for the quantity of heat energy. And there's two ways to calculate Q, the quantity of heat. And the way I look at it is there's a Q when the temperature changes, and there's a Q for when the phase changes. When it changes phase, the T, the temperature flatlines. So the way I kind of remember which equation to use, it really is determined by where I am on those heating or cooling graphs. So let's look at it. So the quiz, it'll be set up very similar to this practice quiz. So here, take a look at number 7 on the practice quiz. Determine Q, this quantity of heat, when 25 grams of water freeze and the temperature flatlines. The temperature doesn't change. The temperature stays at 0. So to help you on the quiz, I will have a little outline or a little sketch of this graph. I'll want you to recognize that you're staying at 0, so the water goes from it goes from a liquid here, and then it freezes, and then it's totally solidified there. So it's just one section of the graph I'm moving through. There is no delta T. So I'm going to use that equation that has mass times delta H. Now remember, we'll use heat of fusion. It's really heat of melting, or heat of freezing for this part. We'll use heat of vaporization for when it's up here at the boiling. So yeah, we'll do it like on the quiz, where I'll just give you one section to look at, and you'll have to recognize that you multiply the mass times the delta H. Okay, so that would be like here. Be able to calculate Q when water changes phase. Multiply the mass times the delta H value. And you'll either be given delta H fusion for when it melts and freezes, or delta H vaporization for when it boils or condenses. And yeah, look at that. Look at that. Delta H vapors, is higher than the fusion. It always takes more energy to boil something than it does to melt something. Now, if you're on the slanted portions of the graph, So like a question like number 8 on the practice quiz. So once again, we'll give you this little outline. Now this is something heating up, getting hotter. So this would be like endothermic, putting heat into the molecules. So on this one, determine the Q, the quantity of heat needed for 30 grams to go from 3 to 100. So I like to mark it on here. There's 3 above 0. Now I get to 100 and then you have to decide, do I stop there or am I going to boil this stuff all the way? Well, it says it's turned all into steam. So here it's liquid. Boil, 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 boil. By the end, that's when it all turns to gas. So there's 2 sections of the graph you're moving through. The slanted portion, I do have a delta T. It goes up 97 degrees. On this portion, it's liquid water, so I use the specific heat for liquid water. And I got 30 grams of it. Now, the flat part, this is where it's boiling. So I'm going to use delta H vaporization. If you look there. And you just multiply that delta H vaporization by how much you have. You get Q for the first part, Q for the second part, and your total Q is just added together. So I think your quiz, it'll be set up the same way, where I'll have you move through maybe one section, maybe move through a couple of sections. And the other energy calculation we'll want you to do is find the specific heat of a metal. Let's go back to the practice quiz. So this is where we would take that cube of metal, cook it, heat it up to like 100, drop it in a styrofoam cup of water that's at room temperature, and then the room temperature water goes up a few degrees, or in this one like 5 degrees. So we'll set the heat energies equal to each other. We know the mass of the metal. We don't know. Our unknown is the specific heat of the metal. But we can figure out the delta T. So now once again, I just take big minus small. That's equal to the mass of the water times the specific heat of water, which we were given. And the water temperature wasn't as much. It only changed by about 5 degrees. So yeah, we do the algebra to solve for the specific heat of the metal. So that's the energy calculations I'll want you to do. Now, I'll also want you to be able to look at or recognize if a reaction is endo or exothermic. And you're given these charts, you're given these tables. You know, a lot of chemistry classrooms have these delta H table or charts and posters hanging up all over the lab. So really what I'll do is I'll describe one of these reactions, and then you just look at the delta H column and say, oh, if it's positive, you're putting heat into the stuff. If it's negative, you're taking heat out of those molecules. So yeah, let's look at where that showed up. Okay, so this is kind of near the end of the practice quiz. But yeah, some things I look for. So like number 22, the synthesis of water vapor. That means you're making it. You're making water. So first of all, I look for water as a product. So water as just water as a product. Water. Oh, here we go. So here's water as a product. There's gaseous water, vapor, steam as a product. There's liquid water. It's supposed to be an L, liquid water as a product. My delta H is negative, so that means it's an exothermic change. So really all you're thinking about is, will this stuff give off heat or will this stuff take in heat? Now, the thing is, if it gives off heat, you feel that. You feel the heat released. All right. Combustion. Remember, combustion's just burning. So, burning something with oxygen. So to burn sugar, we need oxygen. To burn alcohols, you still need oxygen. Really, to light our Bunsen burners, we need oxygen. So when you burn stuff, a lot of times people, if you understand combustion, burning, giving off heat. But you can find those reactions. So combustion is just cooking, burning it. Yeah, there's glucose. There I am burning it up with oxygen. And really, anytime you burn something, you give off carbon dioxide and water. You burn sugars in your body. We're breathing out carbon dioxide and water. That's metabolism there. Just like I said, lighting your Bunsen burner. Here's methane gas up here at the top, reacting with oxygen. That's burning it. It gives off carbon dioxide and water. That's what's released when you burn stuff. That is exothermic. It gives off heat. Ammonia. We'll start using some of that next chapter, but I think ammonia is like a window cleaner. It's basic. It is added to a lot of detergents sometimes. Um, but yeah, so I'm looking, so for this one, this number 25, the synthesis of ammonia. I'm making ammonia. So I'm looking for NH3, NH3, there it is. So find it as a product. That's the one where I synthesize or make ammonia. That's a negative delta H, so it's exothermic. So yeah, that's the other part of this energy piece on the quiz, is be able to interpret that description of a reaction and find its delta H. If you put heat in, it's endothermic. If you take heat out, if it's negative delta H, we classify that as exothermic. All right, some other things I want you to do is compare how well these things stick together. That's what an intermolecular force comparison is all about. If it's solid, solids stick together really well. Liquids are kind of in between, and then gases really don't stick together all that well at all. So, okay. So what was this IMF comparison? What is this all about? Well, I think a lot of times just knowing what the stuff is helps you decide how well it sticks together. Okay, so methane. All right, there's some like methane gas burning. That's CH4. Propane. Propane has 3 carbons in it. Butane. Butane is a 4-carbon molecule. I don't know if you remember, but like butane, what's in lighters? We had our little camping stove going that day. We were eating popcorn in here. That's a liquid there, but really once you depressurize it, it turns to a gas. Same thing with the propane. Once you poke a hole, once you depressurize it, it turns into a gas. Now the gasoline, the cyclohexane we had, that actually stayed liquid. So there's actually 6 carbons in that gasoline, in that cyclohexane, like 4 carbons on the butane, just one carbon on methane. There's 3 carbons on a propane. But these are all oils, fuels. These are all very nonpolar. The only thing holding them together are these London dispersion forces. Those are relatively weak. Now, the bigger the molecule, the more it sticks together. The more liquid it is, the more it sticks together, is really what we're saying. So like the 6 carbons, the cyclohexane, stuck together, was more stuck together than like the butane or those propane molecules could be. So on the practice quiz, here's where it is. So circle the substance in each set with the strongest intermolecular forces. If everything in there's a gas, it's hard to know. Well, how do I know which gas is stuck together better? It's the heaviest one, because the only force holding these are London dispersion. So the heaviest one is stuck together the best. Out of these ones, the methane, the propane, the butane is the biggest molecule. It's the heaviest one. It is stuck together better. So if you're given a list of all nonpolar stuff, just pick the heaviest one. That is stuck together better. Now, if some polar molecules start showing up, all right, and remember what polar is. Polar is things that blend well with water. Those forces are generally going to be stronger than the London dispersion. So, yeah, here is, what is this? Oh, this is a liquid that is polar. This is just alcohol. But yeah, it's liquid. It's liquid here in the room. So it is, and the alcohols are polar. Now, if you've read the soap article, you kind of know how to look at a drawing, decide if it's polar or non-polar. But yeah, that's liquid. That's stuck together better than these gases. Even though ethanol is a similar size molecule, it's stuck together better. How do I know that? Because it's not gassed, it's liquid. So that's an easy way to kind of make that comparison. But yeah, if you see something in there and you know it blends well with water, it's going to be stuck together better than like the oils or the acetones. So yeah, here, look at this. Think about dropping these things on a penny. That's what it comes down to. The water was the most cohesive compared to like the acetone, which was all nonpolar. It doesn't blend with water. The oil, nonpolar. It doesn't blend with water. So even though all of these are liquid, the one that sticks together the best has the strongest intermolecular forces. Yeah, so here, let's look at a drawing of intermolecular forces. Here are some water molecules. Now, we start to draw these little it's actually a lowercase Greek d, a lowercase Greek delta, stands for partial charge. So we say there's a partial positive on the hydrogen, the lone pairs, that partial negative on the oxygen, but that's where this attraction is. That's where that dipole-dipole force, or if it's a special case, like with water, you could call this dipole-dipole. Hydrogen bonds are just a little bit stronger than your ordinary dipole-dipole force. So there's that hydrogen bond between water. I could splash water. I'm breaking the hydrogen bonds. I could boil water. I'm breaking the hydrogen bonds. But yeah, that's what holds the water molecules together. And if it's nonpolar, we don't see those. All right, so how do I know if it's nonpolar? If it doesn't mix or doesn't blend with water, it's nonpolar. That's how you know. Yeah, so some more IMF comparisons. You'll have your periodic table. So iodine solid, that sticks together better than a liquid or gas. And you can tell iodine solid because it's, on your periodic table, it's black ink. Bromine is written in blue ink. It's a liquid. Chlorine's written in red ink. It's a gas. So the solid is stuck together better, stronger IMFs. Hopefully you can recognize salts. Look for a metal and nonmetal in the chemical formula. That's how you know it's a salt. The salt will always be stuck together than, like, say, our natural gas and methane than liquid. So the solid stuck together better. Hopefully you recognize sugar, glucose. It's solid. It looks like sugar. It looks the same as sugar would here in the room. It's stuck together better. Once again, there's that blue salt we used, salts that stuck together better. Ordinary table salt. Now, how did I know this salt was stuck together better than, say, the wax? Well, think about melting it. All right, the wax would melt a lot easier. In fact, we did melt it in class. A lot easier than, say, the salt, than the which we can't even melt the salt. So even if you got two solids, just think, well, which one's easier to melt? That's the one that's not stuck together as much. It has weaker IMFs. So really just thinking about what these things would look like in the room. And yeah, I'll give you stuff that we've been playing with. So yeah, let's go back to our pictures here. So yeah, what is polar? Well, water's polar, oil not polar. Acetone, not polar. All right, it did not blend well with water. But if I gave you water, oil, glycerin, and acetone, and ask you which one sticks together the best, it's the water. Do you remember having those water droplets on the penny? Yeah. Now, ionic stuff, it's like super polar. I mean, it's super stuck together. Super strong IMFs. It's really, really, really solid. There's that blue salt we used. All right. Once again, we say is it polar? It's water. If it's nonpolar, that's like our gasoline, our cyclohexane. Acetone was very nonpolar. It did not blend well with water. Our wax, very nonpolar. It did not blend well with water. But the salt, our salt did blend well with water. So remember, likes dissolve likes. That's kind of an easy way to remember what's polar, what's nonpolar. And then the whole thing is with soap. Soap has both polar and nonpolar components to it. Now here, this is some soap here, I think, on the bottom, but I think that top layer is still a lot of grease. So, so that's a nonpolar, but the soap part actually has a little bit of both, polar and nonpolar components to it. Excuse me. All right, yeah, there's the soap. So soap is both polar and nonpolar. The lard, the fat was nonpolar. The wax was nonpolar. Our sodium hydroxide. Maybe, I think that's lye. Hopefully you remember dissolving that lye in water. It got really hot. It dissolved really quickly. So yeah, that's sodium hydroxide. The lye was very polar. And in fact, it was very exothermic when it dissolved. And you felt that heat being given off. You felt the beaker get hot when it dissolved. So yes, that lye was very polar. Okay. Sorry. Let's go back to the worksheet. So how does this show up on our quiz? All right, so once again, everything has London dispersion, but it's the only force in the nonpolar. Dipole-dipole or hydrogen bonds are stronger. Those polar molecules are generally stuck together a little bit better. And part of it's because they got more things holding it together, more forces holding it together. All right, but let's look at the polar-nonpolar stuff. So question 17 here. Which blends with water? That's what polar means. The salt blended with water. Obviously, water blends with water. Sugar can dissolve or blend or mix well with water. Our sodium hydroxide, our lye, our sodium chloride, our table, those blend well with water. These don't. All right, these gases bubble up right out of water. The wax separates. The oils, the fuel oils, the gasolines. So all of this, all of these hydrocarbons, they're called, oil and water don't mix. So these are all very, very nonpolar. These are all very oily. All right, all these fuels, all these gasolines, all very oily, very waxy, very nonpolar. Okay, now the soap drawings. So if you've looked at the soap article, so here's a drawing of a soap molecule. Carbons, hydrogens, carbons, hydrogens, carbons, hydrogens, carbons, hydrogens, carbons, hydrogens, carbons, hydrogens, carbons, hydrogens. That's like this. It's like our gasolines. It's like our fuel oils. It's like our wax. It's like our fat. It is our fat. That is a very nonpolar portion. Now, this part with the charge. So here's some little charges drawn on it. That's very, very polar. So just like when we kind of drew the water molecule with the partial charges, those charges showing up in the drawing makes it polar. That's really that's kind of how we diagram. We say the poles or the ends of the molecules have a charge. If they don't have a charge, it's nonpolar. What does not have a charge? Carbons, hydrogens, carbons, hydrogens, carbons, hydrogens. So the oily parts, the fats, the greases, the fuel oils, those are always very nonpolar. Things with a charge, so here's an example of the alcohol that's drawn. Now remember, alcohol blends well with water. All right, here's a little jar of it, liquid. It's really 70%. It's water in there with the alcohol. It blends very well together. But we say it's polar. Water, polar. Well, just knowing they mix well knows they're polar. But look at the drawing. There's a little charge. There's a little charge. There's a little charge. There's a little charge. That means it's polar. No charges. Not polar. When we blend them, and like soap, so soap actually is a little polar and a little nonpolar. And that's really why we say it blends grease and water. That's why you can wash with it. That's why we can use it to get oil and grease off our skin. It's because it blends and mixes with both. Now, along this same line, so let's go back. I know I haven't talked about 11 here yet. So you've seen this graph before. It tells us when things boil. So C is water. How do I know? So here is room pressure. And water's vapor pressure will equal, so water boils at 100. So remember, here's 100 degrees. Go up, go up, go up, go up, go up, hit the line. So this pressure of the water vapor escaping, that pressure is vapor pressure. When it pushes up with enough, when that stuff evaporating, that stuff boiling, pushes up with enough force to overcome the atmospheric pressure, we say it boils. So here, this spot right here, that's the normal boiling point of water, 100 degrees. Chemical B is actually boiling at a lower temperature. Chemical A boils at so A and B boil more easily. That also means they evaporate more easily. Um, it also means they probably smell, because things that evaporate real quickly, real easily, you smell those fumes coming out of there. A lot of times we say those things are volatile. Volatile stuff has a strong pressure of gas coming out of the jar, so you can smell it. You smell the fumes, you smell the vapor coming out. So that's really what volatility refers to. And if something is volatile and it evaporates easily, it has weak forces. Something like water that sticks together the best, water that's the hardest to boil, has the strongest forces. So that's really what's going on with this, is just recognize that A boils at a lower temperature, B boils somewhere in between, and C boils at the highest temperatures, which means C is stuck together the best, which means that you could probably float a paperclip on it because it has a higher surface tension, stronger forces holding it together. All right, so I think that's pretty good. If you have questions, please let me know. I appreciate all your attention, and good luck. Good luck on this quiz, everyone. Really, and even during the quiz, call me over. We'll have all these chemicals out. So if you forget what something is, I'll just bring it over and show it to you. And oftentimes, just remembering what it looks like helps you know how it's going to behave. Thanks for all your time.